This is lecture 11 of the NITheCS SATACS category theory course. What I thought we would look at today is a very important construction that we do with sets and functions. And what we will do now is then to translate this construction in the context of an abstract category. So the construction I'm referring to is the following. When we have two sets x and y, and the function f between them, let's say our function maps these 2 points to the same point in the codomain, and it maps these 3 to the same point. And then the last one, it maps somewhere here. And there could also be further points in the set y that have not been mapped to. Function f induces an equivalence relation on x, which is given by putting all the points that are mapping to the same point in the codomain, putting them in the same equivalence class. So equivalence relation as a set, of course, is a set of order pairs. It's usually called kernel relation of f. It could be written like this, kf. So it consists of all pairs x1, x2 in x cross x, such that f of x1 equals f of x2. And as such, it lives inside the product of x with itself. Now, a product, of course, has two projection maps going back to x, pi1 and pi2. And hence, there are two projection maps going from kf to x as well, which are just composites of this inclusion of kf into x cross x with those projection maps. Let's call these things p1 and p2. I'm going to open up for Carlisle now, and while I do that, I'd like to ask those attending to remind yourselves how we constructed kf as a pullback. I'll be back just now. So you can put it here. So was anyone able to recall how we built the kf as a pullback?
So we need like one object y here, and two objects x and x, and arrows respectively. I think f and f.
That's right.
Yep.
And then in this corner we put kf. So this is the construction of an equivalence relation out of the function. And we can recreate it categorically by consider this pullback. Another way to create it, and in fact, another way to create any pullback is first to take the product of x and x. At this point, we do get a diagram like this. However, the diagram doesn't commute. F pi 1 isn't equal to F pi 2. So we get these two arrows by composing those. And then we take the equalizer of that. Equalizer of F pi 1 and F pi 2. And that equalizer ends up being the pullback. And that's a general fact about arbitrary pullbacks. Of course, you need existence of equalizers to prove something like this, and products as well. So this would be then P1, the composite with pi 1 will be P1 and the other will be P2, just like what we described here at the top. So this pullback is an important thing because this construction of equivalence relation for a map is an important construction. In group theory, for instance, we know it through a notion called a normal subgroup. What happens in group theory is that when X and Y are groups, it's sufficient to know the equivalence class of the identity element of the group. Then all other equivalence classes will actually be of the same size as that one. And they can be computed by shifting this equivalence class along other elements. And so the entire information about KF reduces to a single equivalence class. And of course, normal subgroups are very important in group theory. In ring theory, instead of normal subgroups, we have ideals. And one goes on like that. But in general, for general structures, we don't have this nice behavior that one equivalence class determines the entire equivalence relation. So we consider the full equivalence relation. So this sometimes is called kernel congruence of F. Now, categorically, it's a diagram with two arrows, right? This is how a kernel congruence looks like. And we often draw it this way. Put KF there, we put X, and we put pi 1 and pi 2. Now, there is a notion of an internal relation in a category. And this is going to be an example of that. So what is an internal relation? Well, there are many ways to define it. One way is to say that it's just a monomorphism going into a product. And this could be a product of X and another object, X prime. And let me remind you what a monomorphism is. So a morphism is a monomorphism when you've got two generalized elements U and V. In other words, two parallel arrows going into the domain. Mu equals MV implies U equals V. So it's just definition of injectivity in the language of generalized elements. But this definition requires for us to have products in the category, and I can also define an internal relation without utilizing products. The thing is that you can split up the M. Let me actually call this R instead of M. So it's the same symbol as the name of the object of the relation. So we can split this R up into two components, R1 and R2. These are composites of R with projection maps. And then saying that R1, R2 map composed with U equals the other one reduces to saying this component-wise, because indeed this composite will equal R1U, R2U. We actually encountered this at some stage. And so saying that this equals the other one, which is R1, R2V, which is going to be R1V, R2V, saying these are equal, is of course equivalent to saying that R1U equals R1V and R2U equals R2V. So now our definition of monomorphism becomes that when these two things hold, it must imply that U equals V. Okay? And you see this definition now, we stated this way, no longer requires existence of products to state it. So this this is definition for an internal relation. So when this holds, we say that this diagram given by R1 and R2 is an internal relation in a category. Does this make sense, Alexander?
Yeah, it does.
Now we want to test our kernel relation, or kernel congruence, whether it's an internal relation or not. There are two ways to do that. One is to directly use this approach. So then we'll be testing it with this pullback picture. The other is to use the other approach. Then we'll be testing whether this morphism into the product is a monomorphism or not. Now it turns out that for any pullback, this is always internal relation, and for any equalizer, it's always a monomorphism, and we can easily show that just now. But before we show that, I want to also say that there is a different terminology that's also used for this property. It's also said that R1 and R2 are jointly monomorphic, jointly monic, in short.
Does that mean their product is one?
It means that this is a mono.
Okay.
But when we don't have products, it means this.
Okay.
So why is pullback jointly monic? If I take any pullback, and I've got this. Okay, so I shouldn't have used U and V there. Let's say this is F and G, and I've got these two maps, U and V. So if R1, if P1U equals P1V, which is this part, now I'm using P1 and P2 instead of R1 and R2. If P1U equals P2V, sorry, P1V, then it means that both of those composites can be written as a single arrow going from Q to X. So this is the arrow of P1U, which is the same as P1V. And the same on the other side. Now, can you tell me why this diagram suggests that U and V must be equal? Anyone who wants to say?
Not from the universal property of the pullback.
Yes, it is so. We just need to check that this outer diagram commutes in order to apply the universal property. So is it so that F P1U, let's say, will equal to G P2U? And well, indeed it is so, because already FP1 equals G to GPU. Does that make sense, Alexander?
So can you please repeat why is, for example, P2U equal to P2V?
We are assuming that it is.
Ah, okay.
We are proving, yeah, we are proving that P1 and P2 are jointly monomorphic. So we're assuming that they're equal. And so then by the universal property of the pullback, there must be a unique arrow going from Q to P. that makes these triangles, this one and the other triangle, commute. But we already have two candidates. They both make both triangles commute. So they must be the same then, because there only can be one such. So we've proved that in a pullback, the projection maps are jointly monomorphic. And the same proof, similar proof can apply for proving the equalizer is always monomorphism. So if I've got an equalizer of some pair of maps, A and B, so to prove that this is a monomorphism, let me call it E rather, I take two maps going into its domain from some W, let's say U and B. I assume that EU equals EB. Then again, I have the single arrow going here. Then again, this arrow makes those two equal to each other because it goes via E that makes them equal to each other. So algebraically, AEU will equal BEU because AE and BE are already equal since E is an equalizer of AU. And so there must exist a unique arrow going here, making the triangle commutative. But we already have two of them, U and B, and so they must be equal to each other. Does that make sense, Alexander?
Yep, it's similar.
Yeah, very similar. And in fact, the more general fact is that in a limit, if you've got a limit over a diagram, all of these maps will be jointly monomorphic, the projection maps of the limit. And the argument will be similar if you've got two arrows that are equal after composing each one of them, and you build a cone, you prove that it's a cone because the previous one was a cone, and then there must be a unique arrow here, so these two must be equal to each other. Okay, so we can now see that this kernel congruence is an internal relation, and it kind of nicely seems to model this idea of the fact that on the diagram here, in the set theoretic diagram, the thing we got on the left side is a relation. It's an equivalence relation, so we also need to say what that means. So if I have F here, I've got KF, and I've got these P1 and P2. This triple, KF, P1 and P2, is an internal relation. But moreover, it's actually an equivalence relation. Now, we can define an internal equivalence relation as an internal category at the same time. But the lecture we had on internal categories was quite technical, and maybe some of you haven't attended it, so we're not going to do that. I will still remind you of the picture though. So we've got this KF. These are the projection maps, and you can think of this now as object of objects of an internal category and object of arrows, and these are the domain and codomain maps. Reflexivity of the relation says that there is an arrow this way. For every object, there is a arrow, the identity arrow, the choice of identity arrows. And what about composition in a category? Well, composition is given by this pullback of composable arrows, but composable arrows are exactly the pairs for transitivity axiom. With the pullback over X. So the composition map is going to be exactly the transitivity law. And then we also need symmetry. So it's not just an internal category. It needs to be actually an internal groupoid. A groupoid is a category where every morphism is an isomorphism. So every morphism is to be reversible. So the diagrams now the diagrams that I will draw that ensure all of this will be instances of the diagrams we need for defining an internal category, or more precisely, an internal groupoid. So they're not going to be new diagrams, but since we agreed not to refer too much to the previous lecture, then we're still going to draw these diagrams. And we also, I think we also discussed that these diagrams can be obtained using the language of generalized elements in a different lecture. So let's quickly write them out. Reflexivity means that if I go into, I'm going to use, maybe I shouldn't use products. So reflexivity means that if I take the identity morphisms, 1x and 1x, and there is this factorization. So that ensures that KF will contain all the pairs of the form XX. Is that, do you see that, Alexander?
Yep.
Okay, great. Symmetry. So how would I write down symmetry? Do you want to suggest, or anyone? How would I express symmetry? Symmetry, element-wise, says that if X is related to Y, then Y will be related to X. Now, this is the set of all pairs which are related, but I want to also consider the set of all pairs that are related in a twisted way. I could take the same set, but then twist the projections. Put P2 here and P1 there. And then say that there is a factorization. So what will this ensure? So if now I'm working with these as sets, or with generalized sets, so if I've got xy, it will be mapped to here, it will be mapped to y, and there it will be mapped to x. But now, by this dashed arrow, there is some pair here whose first projection is y, and second projection is x, and yet it's in KF. So when x and y are related, then y and x are also related. That's what the condition states. Alexander, is that fine for you?
Yep, it seems totally reasonable.
And finally, to express transitivity, then we need to form, so transitivity says that x is kf related to y, and y is kf related to z, implies x is kf related to z, right? So we want to build this object, triples x, y, z, such that this holds. And then from there, induce that x and z should be inside the object kf. So, and that is done by pullback, because it's like taking these kinds of pairs and saying that this component of that pair should be the same as that component of the other pair. And if you remember the description of pullback, that's exactly what they do. So we take KF, we take second projection to isolate the y. We take another KF, this another KF represents now YZ. We take its first projection, and then we take the pullback. It will be pullback of KF over X. So theoretically, as a set, if this was in the category of sets, or if we're looking at generalized elements, this thing will consist of exactly pairs of things coming from there and there, right? As we said, pullback embeds into product, so it's pairs of something here and something there. But it is such that the second component of this pair matches with the first component of the other pair. So technically, it's x, y, y prime, z, but then we're saying that y must match with y prime. So in other words, this is exactly the set of x, y, z's, where x, y is related and y, z is related. And now we're saying that I should map this to XZ. But to say that means that if I now take the first pair and take the first component of it, which is X, so take this composite here, and I map the triple, I map there, and I take its first component, so I took another P1 here, then this diagram should commute. Can you see that, Alexander?
That's just saying that the first component needs to be
Yeah.
X.
Yeah. Can you see that or not yet?
Yeah, I do.
Okay, fantastic. And then the same also on the other side. So if we take now this composite, it must equal that dashed arrow composed with phi2. And that's ensuring that this Z there matches with that Z there. Okay, so this is reflexivity of this, specifically of the kernel congruence, but if I replace Kf, P1, P2 with arbitrary internal relation, it would be reflexivity of that relation. Reflexivity, this is symmetry, and this is transitivity. So we've now been able to express the fact that kernel congruence is an equivalence relation. So we can write this down. We haven't proved it yet, though. We still need to prove it. We just stated the definition of what it means to be an equivalence relation. A kernel congruence and I'm not going to use internal every time, so I'm just going to call it is an equivalence relation. So let's actually prove these properties now for the kernel congruence. So let's begin with the reflexivity. Remember, the kernel congruence comes out from a pullback. So I'm going to draw in from this diagram, I'm going to draw in the thing that makes it into a pullback, which is this. Okay, so now I'm looking for this arrow into KF. How can I find an arrow into a pullback? By using the universal property of the pullback, right? We need a cone over that of this diagram. Well, I think it seems like we've got one, right? Look at this diagram here. That commutes. F composed with identity equals F composed with identity. And therefore we get this unique map here. So we proved reflexivity. Now Carlisle is going to explain symmetry. If you don't mind to be part of
I
the
wouldn't
lecture.
mind, but I'm not sure if I'll do it correctly. I'll
That's
have to
okay.
think for a second. It's time to actually draw.
Yeah, you do.
Okay. Thought I'd put that in again. Then we have we have these two commutes, right?
Why does it commute?
Because it's the
You want to write it out algebraically?
I can try. That P2 F equals P1 F.
So how do we know that's true?
Is it not just from how we define the kernel congruence?
Yes, except that we had it the other way around. Also,
Okay,
your
yeah.
composites, I think, should be the other way around.
Oh, okay.
You're happy with that, Alexander?
Yeah.
And this means that we have the unique map going from KF2.
Yeah. Great. Thank you very much. Well, so that's symmetry. And now let's look at transitivity.
Can you show us symmetry once again?
Sure.
Thanks.
So how about transitivity? So once again, we want something into the pullback. So we draw the diagram that makes it into a pullback. So we draw these things here. F and F. And in order for me to find this dashed arrow, I just have to check that this diagram commits, right? So let's see why it commits. I can draw another F here, can't I? I can draw in another F. This commits, that commits, that commits. So the big thing will commit. So that's the final category here is playing with this diagram.
Yeah.
We can also write it out algebraically. So you've got F P1 pi 1 that you can rewrite as F P2 pi 1 by FP1 being equal to FP2. But then, because this commutes, we now have that's the same as FP1 pi 2. And then you again rewrite FP1 as FP2. And we get what we wanted. Alexander, you're happy with that?
Yeah, as well.
Fantastic. So we've now proved this theorem that a kernel congruence is always an equivalence relation. Okay, we want to take a next step now. So we've got this equivalence relation, and what happens if we take the coequalizer of P1 and P2? So let me remind you the set theoretic picture. So this is the set theoretic picture. And what I'm asking now is, what happens in the set theoretic picture if we take the coequalizer of P1 and P2? So formally we write it this way, but I'm going to very soon change the notation based on the answer to my question. What construction is this of taking that coequalizer?
It will be very similar to KF itself, because that's the thing where we take all the connected components, right?
We did have a lecture where we did computation of coequalizers and sets.
Yeah.
We spoke of the fact that every element here gives rise to two elements there and there, and we want to stick them together.
So it will be like the minimal induced equivalence relation. Equivalence.
Well, KF is already the equivalence relation. But now, things that are in the same equivalence class, we will be sticking them together.
So it'll be the partition.
Yeah, it will be the quotient set.
Great.
Nothing other than the quotient of x by that equivalence relation by the kernel convex. And that's categorically how we interpret quotient. How do you quotient as an object by an equivalence relation? Well, this way, you put the two morphisms of the relation and you take its coequalizer. On this picture, we're going to get 3 elements in the quotient set. Do you agree with that, Alexander?
Yeah.
So coequalizers are often drawn with this double-headed arrow. Sometimes it's just used for epimorphisms. Epimorphism is dual notion to monomorphism. It's easy to see every coequalizer is an epimorphism. So epimorphism would be that if I have 2 morphisms here, composites are equal, then those 2 must be equal. And again, by the universal property argument, that's true. But coequalizers are, in general, stronger than just epimorphisms. There are special kinds of epimorphisms. Now, in the category of sets, when we do this coequalizer, we observe something very interesting. That this coequalizer will embed into the set Y. Can we draw this embedding in the general category setup? Is there a morphism going this way?
I want to just apply F to something like class.
Remember, this is a morphism going out of a coequalizer. So by the universal property, if I want something going out of the colimit, I just need a cocone over my diagram that is in the colimit. And F is indeed such a cocone because Fp1 equals Fp2.
Okay.
Why is it funny?
Because I don't think I was here when the limits and codes were discussed.
Okay. Yes. It's the dual argument to what we did here.
Okay.
So Fp1 equals Fp2, and by definition of coequalizer, there must be unique error here, like a triangle committed. But is that arrow a monomorphism? Because in the category of sets, it is. It always will be. It's the first isomorphism theorem for sets. Yeah. Is that arrow in general a monomorphism?
I will say yes.
Well, it turns out that in general it isn't, but I can't give a counterexample immediately. Because in almost all concrete cases, it will be.
Okay.
However, there is an interesting result that if every pullback of the coequalizer is still a coequalizer in the category, then you can prove that this is a monomorphism, and it's a highly non-trivial proof that it has.
So every pullback of the coequalizer is a coequalizer.
Yeah. So let's call this thing M, and let's say make a remark here that we do not know whether M is a monomorphism. So is M monomorphism? We can prove that it is when every pullback of a coequalizer is a coequalizer. Before attempting to prove that, let's talk about this condition itself. Why would I ever want to pull back a coequalizer? Well, it turns out that in the category of sets, coequalizers are nothing other than surjective functions. If I started, imagine if my f was a surjective function, right? It means that these 2 points are not there. But then the coequalizer would give me something that's bijective to my, so this injection would have been bijection, and so my original, because coequalizers are unique up to isomorphism, my original f would also be a coequalizer. Now, in the category of sets, if I've got a surjective function, so let's call this x q, and I have any other function here, maybe h, and I take the pullback. So in the category of sets, this is given by the set of those pairs wx such that h of w equals, let's call this map q, equals q of x. But projecting such a pair to w will certainly be a surjection if q was a surjection. Why? Well, I'll pick an element in w. So I'll pick an element in w. I'll map it there by h. Because q is a surjection, there is something from x mapping to that by q. And now I've got two things, w and x, mapping to the same place. And so they give rise to an element in the pullback, which maps here and there. So in the category of sets, coequalizers are stable. This is called stable under pullbacks. When pullback of a coequalizer is a pullback, is a coequalizer. But actually, exactly the same argument can be used for all sorts of other mathematical structures. In fact, for algebraic structures, coequalizers always end up being surjective homomorphisms. And by the same argument, their pullbacks will also be surjective homomorphisms. In fact, this property is shared by many categories in mathematics, especially the algebraic ones. It is an important property, therefore.
Is there a name for categories that sort of have an underlying set structure?
They're called concrete categories.
Okay.
You've got a functor to the category of sets.
Okay.
You put some axioms on this functor. It is an important property. And to show its usefulness, we will now use that property to prove that when that holds, M will indeed be a monomorphism. And the proof is absolutely spectacular. So we have to, the whole idea of the proof is to draw a very specific type of diagram. We take Y, we draw M.
So can you please repeat before what we are going to prove exactly?
So this property that pullback of a coequalizer is always a coequalizer, we're going to prove that this property forces the M here to be a monomorphism.
All right, fine.
as a way. So the reason why we're doing this is we want to show you the usefulness of this property. And I mean, one can prove many other things from this property, but this will be the first thing we want to illustrate its usefulness on. So let me call this thing Q for short. So the co-equalizer we had here, let's call that thing. Okay, actually we can call it X/KF. And then we also draw that unique, no, the map Q, the co-equalizer map. We can call this in short Q because of quotient, small q. So that's our co-equalizer now. And then we start taking pullbacks here. So we form this pullback first. It will be over Y. Then we form another pullback on the left side here. And we're just going to call them P1, sorry, P2. Another pullback and yet another pullback here. P1 cross P2 over that thing. So I'm just going to call it P3. So each of these squares are pullbacks. That does make the entire big thing a pullback as well. And that pullback is something we already have up to isomorphism, so we can actually use that one. So it will be the kernel relation of F pullback because this composite is F. Yes?
Do you mind writing out explicitly what P3 is?
I'm not going to do it anymore because I'm going to call it KF.
Okay.
So I've got this pullback of F and F, right? This is my P1, small p1, and small p2. I can build it by taking these three pullbacks and then pullback of this. Okay. When I build it that way, so when each of these are pullbacks, there is a general fact about pullbacks. We left it as one of the exercises, I think, that you can paste pullbacks together. So if all of the four are pullbacks, then this big thing will be a pullback as well. But this big thing downstairs has F and F because Q composed with M is F. And so we already have another pullback for that, that's the KF. And so the two pullbacks are isomorphic. And so, but pullbacks are always defined after isomorphism anyway, so I can just call this thing KF. Does that make sense, Alexander?
Yeah.
Okay. Now I want to prove that M is a monomorphism. And I don't think I remember how to do that. So we'll have to discover it together. So one thing that's important to keep in mind is the following. So something that will be useful in this proof. An equivalent definition of a monomorphism. A morphism M let's say from A to B is a monomorphism if and only if this thing is its kernel congruence. Well, set theoretically, this is obvious, right? A map is an injection if and only that equivalence relation we create out of it is discrete. But also, categorically, theoretically, we can easily see why this is so. If I draw my A and B and M, and I draw this diagram, which is a cone over M, right, with identities. Now, what does it mean for this to be a pullback? It means that if I have anything else and two maps making MU equal MV, then there should be unique arrow here. But the existence of this arrow, because of this identity, is equivalent to saying that u equals v. Because this arrow, on one hand, have to be equal to u, on the other hand, it will have to be equal to v. So just by just the definition, basically, of this being a pullback is exactly the definition of M being a monomorphism. And because pullbacks are unique after isomorphisms, this also can be equivalently stated that we want to prove that in this pullback that we've got here, that these morphisms are actually isomorphisms. Then they will end up being the same isomorphism as well. Sorry, no, they am I right in that saying that? But they will end up being the same isomorphism. Let's quickly check that.
Will they even be isomorphisms? So it's a question squared. Back to the question.
No, I'm saying that if I want to prove that M is a monomorphism,
yeah,
it's sufficient to prove that yeah, I think I want to say something even stronger. It's sufficient to prove that these two maps are actually equal to each other. Let's actually work that out. So what happens when so yet another equivalent formulation of being a monomorphism. Imagine you've got your morphism M such that the kernel relation, the kernel congruence, has both projections equal to each other. So there is this K, and you got, let's say, R and R. So to say that something like this is a pullback is equivalent to what? Well, having U and V again, such that MU equals MV. We now say there is a unique map here. Okay, so let's call this thing W. Now RW on one hand equals U, on the other hand it equals V, which makes U and V equal to each other. So if this thing is a pullback, M definitely will be a monomorphism. On the other hand, if M is a monomorphism, then we already know this is a pullback. So it's a pullback of this kind. So that proves the equivalence. Okay. So what we're trying to then prove here is that these two morphisms are equal to each other. And we have to use the assumption we have that coequalizers are stable under pullback. So not only we know that this thing is a coequalizer, now we also know that this thing is a coequalizer because it's pullback of the other one. And the same goes here. And then also we know this is a coequalizer and that is a coequalizer by stability of coequalizers under pullbacks. Would that make
identity going from
what would that make the composite? So the proof, I think, makes use of that composite somehow. So let's think about that. Oh, we have 1 hour to think about it, so plenty of time. So just to make sure, Alexander, are you on board here?
Yep, of course.
Okay, no, I'm just asking whether maybe something was too quick here and that you're comfortable with where we are now.
I am actually.
Okay, great. So let's first of all maybe give these things a name. Let's call this R1 and R2.
What is P1 and P2? Big P1.
These are the maps coming from the kernel congruence.
No, but the objects. I mean,
Yeah, they're pullbacks of this and the other, and
Okay.
the other one respectively. This is a very fun result because every time I reprove it, after that I forget it. And so every next time it's a fresh experience.
well, the orange arrow.
What about the orange arrow?
I'm just trying to understand this first. So theoretically, will that arrow just send a pair to the product of the two classes that the respective elements end up in? Not the product of the pair of the classes.
That's a good question. What will that? Yeah, okay, that's a good question. So, yeah, because projecting with R1 gives me P1Q. So it's the class of the first component and the class of but they must be the same, right? The class of the first component and the class of the second component must be the same.
Oh yeah.
So that's what it must actually send it to the two same things.
Yeah. But then it's not
And that's
surjective.
Yeah, then it unless this is just the same as just one of them.
Yeah. Okay.
So that's exactly kind of it can maybe it will help us to prove.
Okay.
We want to get convinced that
Yeah.
I mean
yeah,
we know
okay.
it's surjective, so
Okay.
so
I see.
that
Yeah.
so I don't know if this will be helpful, but in general for any pullback we always have diagonal map. So whatever pullback we have, we can always put here the same A and identity here and make it commute, and that will give the diagonal map there. So here too we've got something going up here. We can call it delta and it's the same delta that goes up here, and this delta has the property that R1 composed with delta is identity, and also the same for R2. So in trying to prove that those two things would have been the same, I could try to prove that, I mean, in trying to prove that R1 is an isomorphism, I could try to prove the other composite is also true, that delta composed with R1 is also identity. Then delta and R will be isomorphous, will be inverses of each other. And since it's the same delta here and there, then R1 must be equal to R2 as well. But to prove that, it would be, because E is an epimorphism, to prove that, it would be sufficient to prove that delta R1 with E equals just E by the epimorphic property. So if we could prove that, then we could prove that, and then we could. But delta R1E is, if I try to chase along the diagram, so it's E, R1, and then it's going delta, but E R1 is the same as this. So it's that. So why is that the same thing as just E? And maybe we use now the fact that R1 and R2 must be jointly monomorphic. So to prove that this is true, it would be sufficient to prove that they're equal up to when being composed up to both R1 and R2 separately. So since R1 and R2 are jointly monomorphic, to prove these two maps are equal, these two maps are maps going into here, right?
Yeah.
To prove they're equal, it's sufficient to prove they're equal up to being composed with R1 and as well as being composed with R2. So what happens if I compose them, each of them with R1 and R2? So R1 delta R1E, if that equals R1E, and also R2 delta R1E equals R2E, if I can prove that, then I'm done. Then this will imply the other one. Now I need to copy this picture so we can look at the picture at the same time. So all of this comes out from your question. I got this idea to do that after what you asked. Yeah. So in the setting of this diagram, we will be okay. So let's check if Alexander is also on board here. So do you agree, Alexander, with these two implications?
To be honest, I'm kind of lost here.
Okay, so let's begin with the first one. Let's first unpack why we have this implication. The definition of epimorphism is dual to the definition of monomorphism. Okay, if I go back to the definition of monomorphism, where is it now? If I go back to the definition of monomorphism and I dualize it, what do I get? I'm going to get UE equals VE implies U equals V. You agree?
Yeah.
Okay. So, just like an equalizer is always a monomorphism, a coequalizer will always be an epimorphism. Are you happy with that?
Yep, I know it.
Okay. Now, if I prove that this equality holds, then because E is an epimorphism, remember E is this morphism, so it's an epimorphism because it's coequalizer, as we said. If this equality holds, then I can cancel by E, by the epimorphism property, to get this equality.
Yep, it's clear.
Yeah, okay, good. But now, I also know that R1 and R2 are jointly monomorphic, right? Because it's fullback. we proved that in every pullback, the projection maps are jointly monomorphic. We call it jointly monic. Are you fine with that?
Yep, I remember it.
Yeah. So if I know these equalities hold, then I could cancel jointly R1 and R2 to get that equality.
Do you mean by cancel jointly?
So if I go back to the definition of being jointly monomorphic, you see, R1 composed with something equals R1 composed with another thing, and R2 with those two things are also equal, then the two things are equal. That's the definition of jointly monomorphic. So it's exactly the same pattern here, where we have R1 composed with U, R1 composed with V, R2 composed with U, R2 composed with V, and then we're deducing from this that U and V are equal. Are you happy with that?
Yeah.
So think of this as, if I literally copy paste this thing, it's exactly what we have here, with the underlying ones, arrows being the ones that match with each other. So now we are trying to prove, we've reduced the problem to proving this. Or maybe I haven't yet explained why this gives us that M is going to be monomorphic. We're going to come back to that. First, let's prove this, and then, but actually, no, let's first explain why this will imply that M is a mono. Okay, so now we are unpacking this implication. Okay, just to double check. So, Alexander, you happy with these two implications so far?
Yeah.
Okay, now let's unpack this implication.
So we were trying to prove that R1 is equal to R2.
Yeah. So delta, what is delta? Delta is the morphism that comes from the universal property of any pullback. In this case, we can actually draw it as well. So I'm going to draw in where we get delta from. So here I've got X over KF, and I could put identity and identity there, identity morphisms. Then this commutes, and by the property of the pullback, there is a unique thing going there. That's what we call delta. That thing makes the two triangles 1 and 2 commute. And so R1 composed with delta is equal to identity. It's this identity. Same way, R2 composed with delta equals identity. If I can prove that this is also true, delta composed with R1 is equal identity, then delta and R1 will be isomorphisms that are inverses of each other. And R2 is another inverse. It's one-sided, but it's okay. When delta is an isomorphism, one-sided inverse is the two-sided inverse. And R2 being another inverse, that will make R2 and R1 equal to each other. But if R1 and R2 are equal to each other, by what we discussed here, then M will be a monomorphism. Are you happy with that?
Yes, sir.
Okay. So now let's see how we can prove this. And that's, I think, will probably be just a simple chase on the diagram. So we've got here, I'm going to try to draw this. So E, then R1, then delta, then R1, right? And that can be pictured as this, that, and that. But that's identity, which is the same as this, which is the same as that. Good. Now algebraic proof. So R1 delta R1E equals. Notice that R1E is the same as QP1 because of this, right? That equals R1 delta. Wait, it's actually easier than that. Sorry, this one is quite easy. I did it in the long way. R1 delta is identity. We already said that there.
Oh, yeah. Okay.
So this is fine. This is easy equality. Now the other one.
With R1. We don't have delta R1 as identity here.
No, we won't. We're proving that. Yeah. Now let's look at the other one. The other one we've got E R1, then delta, then R2. Okay. That would be the same as going this way. But wait a second. Delta R2 is identity, isn't it?
Delta R2.
Yeah, for the same reason as the other R1, delta R1 was.
No, we didn't have delta R1 as an identity. We only have R1 delta.
Yeah, sorry, yeah. But what I'm saying is here.
That's an
This is an identity. But then we will get that R1E equals R2E.
yeah. Well, that means R1 equals R2.
Because E isn't, no.
But wait, we're trying to prove this.
Yeah, we're trying to prove this equality.
Yeah.
So we don't know yet that those things are equal.
Yeah. If we did know, then
yeah. So let's try another way. So R2 delta R1E equals, let's try to replace ER1 with P1Q. So this Q P1. But QP1 is equal to QP2, isn't it?
fine.
Oh, because Q is a co-equalizer of P1 and P2.
Okay.
That's how we build Q. If I go back all the way, that's too long. Q is a co-equalizer of P1 and P2. So that equals that. And now I've hopped on the other side of the diagram suddenly, right? So now I've got P2Q delta R2. But isn't that the same as ER2? So it's the same way. QP2 is the same as ER2, isn't it? Sorry, I mean R2E. And we're done. Because delta R2 delta is identity, isn't it? Oh, we actually didn't need all of that. I don't think we needed delta. I think it's easier. Look, R1E is equal QP1. QP1 is equal QP2. QP2 is equal R2E. And by the fact that E is an epimorphism, it implies that R1 equals R2. Yay! Alexander, are you happy with that?
Well, that's much easier.
Yes, much easier. But sometimes you have the long way to find an easy way. So we didn't need delta at all. So your idea actually confused us. So help us. Well, that's very unfair because we might not have found the easy argument otherwise. But let's scrap off what we don't need. We don't need any of this. Correct, but not needed. Okay, so we've managed to prove what we wanted, namely that. So now we can state this as a theorem. Actually, we can let me first state a definition. A regular category, you might remember this from Professor Rodello's lectures.
I don't think I attended the
Okay.
lecture.
A regular category is a category having the following three properties. First, every morphism has a kernel congruence. Yeah, I'm going to state a slightly stronger definition of a regular category, which is more useful for various things. What I want to say is that finite limits exist, which is the same as to say that equalizers and products exist, which is the same as to say as pullbacks and terminal object exist. But let me phrase it more in a more standard way. So equalizers, so all equalizers and products and binary products exist in the category. So this is equivalent to saying that all finite diagrams have limits. And second property, that coequalizers of not all coequalizers, but only of congruences. Sorry, of kernel congruences exist. And third is that coequalizers of kernel congruences are stable under pullback. The condition that we use in our theorem.
So the theorem that we proved, is the converse not true?
No, it's not true. And an example is the category of topological spaces. By the way, coequalizers of, coequalizers in general are called regular epimorphisms also, kind of links with the definition of regular category. And then we prove this theorem that in a regular category, every morphism F factorizes as ME, where M is a monomorphism and E is is a coequalizer. So how does one prove such a thing? So we've got F because of property one, because equalizers and binary products exist, we can create a kernel congruence of F. Then, because of the second property, we can create its co-equalizer. That will be E. And because of what we just proved, this unique morphism will be a monomorphism. I want to make a couple of remarks here. In any category, any co-equalizer is always a co-equalizer of its kernel congruence when the latter exists. Talking about co-equalizers of kernel congruences and talking about co-equalizers in general is the same thing because of this. Let's actually prove this as a small lemma. So let's say we've got two morphisms, A and B, and we take their co-equalizer C. Then, after that, let's take their kernel congruence. So KC with P1 and P2. Because CA equals CB, we get this diagram. And then by definition of pullback, there will be unique morphism here. So we get something here, let's call it U, such that P1 U equals A, and P2 U equals B. But now I can prove that C is actually a co-equalizer also of P1 and P2. How? It's very easy. If I have another morphism that makes P1 and P2 equal, that makes these two equal, because of this, it will also make those two equal. And then I'm going to use the fact that C was a co-equalizer of those and get the unique morphism here. So every co-equalizer arises by quotienting out the kernel congruence. And so a regular epimorphism is a co-equalizer. It's another name for a co-equalizer, a regular epimorphism. And what this lemma tells us that you can think of it as just an arbitrary co-equalizer, or you can think of it as something that came out from the kernel congruence. And this theorem that we stated here, one can think of this theorem as the first isomorphism theorem for a general regular category. Just to give you a synopsis of which categories are regular and which aren't. Examples and counterexamples. We're not going to prove them, but just to make a list. So, regular categories and non-regular. So let's play a little game. You name a category, and I'll tell you whether it's regular or not, if I know. So the idea of the game is for you to think of a category for which I will not know whether it's regular or not.
What about the category of the first one you started with, of natural counting systems, or what would you call it?
It's regular. The category of counting systems where the natural number system is the initial object is a regular category. And that's because it's algebraic, and every algebraic category actually is regular. Alexander, you wanted to give it a try?
Well, how about topological spaces?
Not regular. Vector spaces is regular. Abelian groups is regular.
Metric spaces.
Not regular. Metric spaces do not even have products.
Right. Middle category.
In general, monoidal categories are not regular. Topological space is an example of monoidal category. It's not regular. Graphs is not regular. Posets, the category of posets is not regular.
Is graphs, is that the category of graphs, or is that
The category of graphs, yeah.
what are morphisms there?
Graph morphisms, those edge preserving morphisms. You can see from this already that algebraic things tend to be regular and geometric ones tend to be non-regular. The dual of the category of topological spaces actually is regular. Also, the dual of category of sets is regular.
Is there a category with but itself and its dual non-regular?
Yes. Okay, that's a good one. So Carlisle is asking for a category. Is there a category C such that both C and C op are non-regular? So unfortunately, topological space is out. Well, metric spaces is such a category, but it's for bad reasons. I mean, it doesn't have products, and what about co-products, co-equalizers? I'm not sure actually about that. I don't think I'm sure about graphs and posets either, whether their duals are regular or not. Okay, so you win. You asked a question about regular categories I cannot answer immediately. But the answer is yes. I just can't think of a counterexample right now. Maybe I'll come up with one before we finish the lecture. It's actually interesting to prove why topological spaces is not regular. It's not because of the failure of regular epimonal factorization. That still holds, but it's regular epimorphisms that are not stable under pullback.
What are
There are quotient maps of topological spaces.
Yeah,
Regular epimorphisms, not just surjective continuous maps, but quotient spaces, quotient maps. And if you pull them back, you can destroy the quotient map.
have you seen an example of that?
Yes, we can. It's easier to work with posets because, I mean, finite posets anyway can be seen as topological spaces.
Yeah.
So here is an example of a quotient map of finite posets whose pullback is no longer such. Again, I'll have to come up with one together with you. So how about so let's try something like this. If I stick these two together, then I will get this poset, right? So that's an example of a quotient map.
So is the top bubble also the poset?
Yes.
Okay.
Yeah.
So the top part is just not related at all to the.
Yeah. Now I want to pull it back in such a way that regularity will be destroyed. I mean, regularity here means that it's a quotient map, so that will be destroyed. So how can how can a morphism of posets not be a quotient map? By having some relationship that's not forced. Actually, no, this one is a quotient map, but let's first try to come up with a simple example of a morphism of posets, which clearly isn't a quotient map. And then try to represent this pullback. So what would such an example be? This is arrow going down.
Yeah.
But how do you map it then?
This one there, this one there, this one there, and this one there.
Sure. Couldn't we make it simpler? But no, but then these two should be the same, no? The map should preserve the relation.
Which two should be the same?
If this one maps there and the other
No,
one
this one maps there.
where does the bottom one map?
The bottom one must be the bottom one.
I mean this
Which one?
that one.
Oh no, sorry. This is the function arrow.
Oh, okay.
I'm saying this to that. The diamond to the chain.
Right, yeah, that's a good example. And to simplify it a little bit, so let me draw what Carlo was showing me here. We could actually simplify it a bit, right? So we could have this mapping to this. So that would be an example of a surjective function of posets that's not a co-equalizer, because
we should
because this is not forced by what's going on there. Sorry?
I said we should technically get rid of that arrow.
Yeah, we don't need that. I think of as a diagram. But let's keep that nevertheless. Okay, so can we represent this as a pullback? The thing is that this map is already injective. I'm not sure if that's going to give us a problem or not. So here, that thing maps to that, right? And this one maps to this. This one maps to this. If these elements at the top are elements in the pullback, then there must be a counterpart on the other side, right? So this must be mapping somewhere where that one maps there, so that is brought back down here in order for that to be in the pullback. So this is going to be the pullback, this is going to be the left hand side. And the same applies to all of these. So this will map somewhere, and that will have to come from some picture like this, and the same there. But now we can examine what arrows are we forced to have or not. Because there's an arrow here, it must be that there must be an arrow also on the other side, on the other coordinate. So there must be an arrow here in order for that arrow to be there. In the same way, for this arrow to be there, there must be an arrow here. That, of course, forces arrows here and here. But now, this must be continuous. So there must be also this arrow. But if I insert that arrow, then this is no longer a quotient map. Just like this one wasn't, because now so far we've just created an identical copy of that, right?
Okay.
But I think we can still, maybe we can still force this to be a quotient map by inserting more points. So what if we had like another point? No, but we don't want to have this arrow, right? So what if we do this? Okay, that's a problem, because if we do something like that, and we want to kind of, if we want to map these two together, then the pullback will have another element, right? Because now if they map together, this and this two also map together. So I don't want to map anything else to this one. Otherwise, I'll have to create new elements here. And the same goes for that. I don't want to map anything else here. But then how can I force this arrow if I don't map anything there? Can I? Alexander, are you following what we're doing?
Yep, I do.
So when we talk about a quotient for posets, that are we talking about the congruences of kernel congruences of morphisms? Or
Yes, and quotienting by that, yeah. But as we said, it's the same as any co-equalizer. So you just take a poset and quotient it by equivalence relation, and then you force the less or equal relationships in the quotient to be coming from the one in the domain. So maybe what we could do is we could have this, where these two map to the same element. And I think then we're fine. Because then this will be forced and that will be forced and that will be forced. So that's our counter example then.
I'm not sure I understand it entirely.
You made it. So so this is our quotient map of posets. Do you agree with that? That's a quotient map.
Just because it's sticking two things together, or
Yeah, so all the arrows downstairs are forced by sticking things upstairs. So this one directly comes from upstairs.
Yeah.
This one directly comes. This, on the other hand, is forced by transitivity.
Yeah.
And these two are forced by these two that come from upstairs. So this is a quotient map of both sets. Okay, now this is an arbitrary monotone map. We agree on that. And now do we agree that this is exactly the pullback? Well, which pairs are the ones that go to the same place? So these 2 points go here, and there's nothing from the left side going there, right? So this will not contribute to building the pullback.
Yeah.
Only these ones do.
Yeah.
But these ones map injectively, and also those map injectively. So that pullback must be the same as that.
Yeah.
Do you agree with that, Alexander?
Yep, I do.
Mm-hmm.
So it's interesting. I wonder if there's a connection. So the reason I gave this example is because I know this is also an example of a bijective poset homomorphism, which isn't an isomorphism. So I wonder if that's and in topological spaces you also have that you have homomorphisms.
Yeah.
Which are bijective but not.
Yeah. That phenomenon is related to this indeed, yeah. But let's look at that in detail. Let me just first write this up. This shows that coequalizers in the category of posets are in general not stable under pullbacks. So there is another interesting phenomenon that comes from the same example that Carlyle is observing, that in the category of posets, there are morphisms that are both epi and mono, yet they're not isomorphisms.
No, well, I think same goes for topological spaces, actually.
Yes, the same is true for topological spaces, indeed. Now, what cannot happen is for a regular epi and mono not to be isomorphic. Regular epi plus mono implies iso, and that's easy to see. If I have a coequalizer which happens to be mono, so if E is a coequalizer plus mono, we already said in the previous theorem that a coequalizer will be a coequalizer of its kernel congruence. So then EP1 equals EP2, where P1 and P2 come from the kernel congruence. But being a mono, it means that P1 equals P2, right? Okay, but now E is a coequalizer of two equal arrows. Identity always coequalizes two equal arrows. If these two arrows are equal, then identity composed with each of them are the same. But then there must be unique arrow here. Let's call it E. Let's call it M. And we have that M composed with E equals identity. So now we've proven that E has one-sided inverse. But actually, it's going to be the two-sided inverse, because E composed with M, I'm going to prove is also identity. To prove this, I'm going to use the fact that E is an epimorphism. So I'm going to prove that that composed with E equals identity composed with E. But because this is identity, the left side is E, and the right side is obviously E. So that's how one proves that E is an isomorphism.
So does every non-regular category have?
And sorry, in this argument, we actually didn't need to go through the kernel pair. So we could have done the same thing with A and B. If I put A and B here, the same argument works. And E coequalizes two equal things, and so on and so forth. So I overcomplicate the argument a bit. Your question?
So does every non-regular category have such a morphism? A epimono that isn't isomorphic. So is that like a characterization, or is it just coincidence?
Okay, so here's an interesting question that Carlyle asking. Does every non-regular category have a non-iso epimono? Okay, first of all, you get regular categories in which there are epimonos, they're not isos. Okay. The category of rings is such. Insertion of integers into rational numbers is both a monomorphism and an epimorphism.
How do you? Why is it negative?
Is an epimorphism in the category of rings, because here everything is an inverse of something coming from there. Okay. And you can use that to prove that if two maps going out are equal on the integers, they must be equal on the matrices as well.
Yeah.
So what I stated here in this theorem was that regular epi plus mono must always be iso. And that's true for any category, not just a regular category. Epi plus mono doesn't have to be iso. Even in a regular category, it doesn't have to be iso. But let's go back to your question. You're asking if I take a non-regular category, is it possible that what is an example of a non-regular category where we have a non-iso? No, you want an example of a non-regular category
Or every
where every mono is iso.
or
Yeah. So here is the answer is no. Take the category of groups, but it's dual. It's non-regular. Epi is there in the category of groups, and this is a highly non-trivial result. It's an exercise in the MacLean's book, Categories for the Working Mathematician, to prove that every epimorphism in the category of groups is actually the same as a regular epimorphism. So epimono in this category are equal to isos. And that's so. How do I know that? Because epimono in the dual category is the same as in the original one, because it's a self-dual concept. So I was able to answer this question of yours. And am I able to answer the other question, which is whether there's a category such that both C and C op are non-regular? I feel a bit embarrassed that I cannot answer because it's definitely many of them.
What is the opposite of posets?
I think because of topological spaces opposite being regular, I think posets opposite will also be regular. That's my impression. Could be wrong. Yeah, I want to think of an example where I already know that it's the case. We could have tried to prove this, but and yet I can't. Okay, well, we'll have to keep that for the next time then.
Until when are these lectures going?
Forever. No, it's not forever actually. Yeah, we will be soon wrapping up. Maybe we'll have one more.
Yeah.
Any questions from your side, Alexander?
No, not really. That was quite interesting, actually.
Yes, so let's actually summarize a bit what we did today. What we did today was a bit different from what we did other times. Most of the other lectures we would define new concepts and trying to understand them. Today we try to prove things using some of the concepts we have defined. And these arguments we gave here, I mean, the definition of a regular category and so on. Maybe I should actually tell you something about the importance of regular categories in conclusion. So you get these categories that are good for algebra, algebraic categories, but not just algebraic, also quasi-algebraic categories and so on. And then you get categories that are good for logic. There's something called a topos, for instance, which is a universe inside which you can do mathematics, just like in the category of sets. And then you also get categories which are good for geometry. Let's say topology rather. And regular categories absolutely encompass the bottom two. So they're central to categorical algebra and to categorical logic. They only partially encompass this, and when they do, it's always in dual sense. So, like topological space is dual as a regular category. It's almost an accident. Even though I couldn't come up with an answer to your question. So for algebra, regular categories are of fundamental importance, and also for logic. And the kind of logic, the kind of math, you can actually already in a regular category, you can do some mathematics. You can treat a regular category as a universe for doing mathematics. But there is only certain kinds of first order statements you can use for such mathematics. And they are statements of the form that exists something implies there exists something else. So there exists something such that some atomic formula consisting of conjunction of atomic ones. So this would be actually conjunction of atomic formulas by atomic, and another conjunction. And then all the free variables that you've got, you quantify them here outside. These are called regular formulas because of regular logic. There's quite a lot of mathematics you can do just with these. All of algebraic derivations are such that, for example, you don't even need the extension to quantify them. So as long as your mathematics uses matrix of regular logic, then you can do it inside regular categories. But it's interesting that also the categories from algebra tend to almost always be regular categories. So they're very important structures. You wanted to say something? No. No. Okay. Okay, great. So I think this brings us to the end. And also one other thing I wanted to tell you is that in terms of this direction, this field is called categorical algebra. And in terms of this direction, this is called categorical logic.
So what exactly is categorical logic? What's the...
Well, category theory is a bit like X-ray glasses you can put on yourself. And then with these glasses, you can look at anything. And what you see will be that thing categorical. So in categorical logic, you first of all want to define what is first order logic, but do it categorically. And it actually is a very elegant construction. You define it as a kind of a functor. We talked about this in the logic course so that you partially attended. Then you also want to talk about silence and completeness theorems. And again, every concept of logic is phrased in the language of categories, which makes it quite versatile in a different way, and also proofs become, in a way, simpler. And then you also want to, so one of the big questions that was completely clarified by categorical logic was, what does it mean to do mathematics intuitionistically? So when we don't have law of excluded middle. So the answer to that is, it's exactly the mathematics that you can do in an arbitrary topos. Topos is a special kind of irregular category. So instead of just having a logical system that gives the answer that says, okay, it's the mathematics you can do with this logical system. The answer is that's a equivalent answer, but another way of looking at it is exactly the kind of mathematics you can algebraically do inside the topos internally. And then categorical logic also has been connected with geometry via the same toposes. Toposes were actually introduced in the beginning as a way of generalizing what a space is by Alexander Grothendieck. And then it turned out that toposes which are good for logic are also categories that are good for geometry, specifically algebraic geometry. So on one hand, categorical logic relooks at all of logic, all of mathematical logic. Like that, it doesn't skip anything. Even model theory is part of. There is categorical model theory also. On one hand, it does that, but on the other hand, by doing that, it reveals new links that before were not possible to establish. And one of such strong links is that with algebraic geometry. There is a book by MacLean and Mordyke, which is an introduction to toposes from both lenses, from algebraic geometry lenses and categorical logic lenses. One of the things they do in that book, towards the end of the book, they explain how to present Cohen's forcing method for continuum hypothesis using the ideas from topos theory. But they do say at the end of the book that one has to still, there's something still to be refined in that direction. I don't think anybody has taken up on that yet.
Oh, wait, specifically on the forcing.
Yeah.
Okay.
There is something that categorically unnatural is happening. Something seems to be forced too much, which maybe that's why it's called forcing.
That seems like a very interesting direction of research.
So categorical logic is a very powerful tool. Also, it has a very, very strong link with computer science. It's another area. Type theory, for instance, is to express type theory properly, you eventually end up using categories. By properly, I mean algebraic. It gives a nice algebraic semantics for type theory. Okay, so I think that brings us to the end. Thanks those who are here, online or in person, and see you next time.
Goodbye. Have luck.
Bye.